family mode.
Hello, everyone. I'm Gail Warren with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Sean Maxwell and Joe Seabrick joining us today to talk about key challenges in multifamily building ventilation and strategies to address these challenges. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin you should use to dial in. Panelists, we ask that you please mute your audio device while you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you would like to ask a question, please use the questions pane to type in your question. Please indicate to whom your question is addressed. You may find PDF copies of the presentations at the website listed here, and you can follow along as our speakers present. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting agenda prepared for you today that will focus on challenges in multifamily building ventilation and strategies to address these challenges. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we will have a Q&A session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for nearly 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. This is applied research to deliver building science solutions using a 4-step framework. These innovative solutions are tested in homes to develop proven case studies of success the market can point to. Building America provides the tools the building industry needs to ensure the innovations are applied correctly, always keeping an eye on energy performance, durability, quality, and affordability. The final step, infrastructure development, is the conduit to getting into innovations to the marketplace. Building America research focuses on how the components of new and existing homes work together through systems integration. As the market changes and evolves, so has the direction of our research in order to add value and drive changes in performance across the residential building industry. In addition to technical challenges we have been addressing for decades, there is now a need to understand market transformation issues such as valuation of energy efficiency to our portfolio. In the nearly 20 years of Building America research, we have spearheaded combining ultra-high efficiency with high performance in both new and existing homes, and we are consistently achieving this challenging task. For example, in 1995, a typical home used 3 times more energy per square foot compared to today, and indoor air quality, comfort, and durability problems were common. Today, a home built to DOE Zero Energy Ready Home specifications uses less than half the energy and is more comfortable, healthy, and durable. By 2030, Building America will demonstrate that new and existing homes can produce more energy than they use. Do you want to know more about these proven innovations born out of world-class research? The Building America Solutions Center is your one-stop source for expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. You can find it by the URL on your screen or by searching on Building America Solutions Center. Also, the Building America website provides information about the program, the latest top innovations and case studies, and also there you can subscribe to the monthly newsletter. And now on to today's presentation. Our webinar today will focus on challenges in multifamily building ventilation and strategies to meet those challenges. If you would like more detailed information about any of these efforts, or if you are interested in collaborating, please feel free to contact any of our presenters. Our first speaker today is Sean Maxwell, a senior energy consultant at Stephen Winter Associates. Sean is a certified energy manager and works primarily in multifamily buildings. Recently, his work has focused on cost-effective retrofits, including innovative approaches to repairing central exhaust systems. Today, Sean will discuss a field evaluation of passive vents as a makeup air strategy and offer design guidance to improve their performance. Next up is Joe Stebrick, who is the founding principal of Building Science Corporation and an adjunct professor of building science at the University of Toronto. His work at BSC includes providing expert witness testimony, overseeing research and development projects, and writing for buildingscience.com. A building science pioneer, particularly in the areas of air barriers, vapor barriers, and vented and unvented assemblies, his work has impacted building codes and practices throughout the world. Dr. Stebrick is also a noted educator and author of the best-selling Builder Guides. Today, Joe will present several balanced ventilation options that meet the ASHRAE Standard 62.2 2013 ventilation requirements and various air sealing compartmentalization options that meet the current and proposed requirements. With that, I'd like to welcome Sean to start the presentation.
Hello, everyone. I hope you can hear me okay. My name is Sean Maxwell. I'm with Stephen Winter Associates, and I have to confess that I'm really thrilled to be on this webinar with Joe Stebrick, who's absolutely one of my heroes for the past 10 years, so it's a real honor. I'll go over our research in multifamily ventilation and compartmentalization. So in the past, over the past few years, we've been doing research on compartmentalization and ventilation and their interaction. And the main question we've been asking is, since in New York City, where we mainly work, we have a lot of buildings with exhaust-only ventilation, or at least exhaust ventilation. We want to know, where's the makeup air for that exhaust coming from? So a pretty simple example is a single-family home where you have an exhaust fan that's pulling air out of the home. Where's the air to replace that coming from? We generally assume it's coming from the envelope, and so that's the basic question we're trying to answer for multifamily buildings. So we want to know, where's this makeup supply air coming from? So in some buildings it's pretty easy to tell. Centrally ducted supply, like an ERV, it's easy to measure and verify that there's air coming into the unit. We've also tested buildings with door undercuts as a means of makeup air. Corridors are pressurized and the units are depressurized, and air is supposed to make its way under the corridor door. And we've tested a novel PTAC unit with a fresh air kit that has a small fan that's supposed to pull air from outside through the unit and deliver it indoors. And finally, we spent a lot of time looking at passive vents. So passive vents include things like trickle vents and airlets and all sorts of other vents that are supposed to draw air in through the envelope. So what we're trying to do is quantify these airflows. The easiest one to quantify is the exhaust fan. So we can measure that, and we know that all the air that leaves the apartment through the exhaust fan has to be made up from somewhere. So some sources of makeup air, like trickle vents and the exterior envelope, we'd probably call those good sources of makeup air, but some of the other sources would be less desirable. So airflow under the corridor door is not good, and airflow through the corridor wall is not good, and also airflow through interior walls, floors, and ceilings from your neighbors is not good, but all of those equal the flow from the fan. So when we're trying to show what's adequate makeup air, we have to come up with a term to express this, and we just called it controlled makeup air fraction, which is the amount of makeup air provided by, say, a trickle vent, which is a known source of fresh air, over the air removed by the fan. So in a balanced ventilation system, the controlled makeup air fraction is 1. So there's, for every unit of air that's drawn out, there's 1 that comes back in. So for just, we don't really have a measure of what's considered good, but if just for the purposes of this presentation we call 50% of makeup air coming from a known clean source as good, we'll consider that good enough for this presentation at least. So typical exhaust-only strategies in multifamily buildings rely on having equal pressure in all of the apartments, drawing air out of the apartments and air coming in from other places to make up for it. This is a pretty common scheme you'll see in this presentation, which is 3 apartments in a row and a corridor in front and the exterior in the back. So when you have 3 apartments and they're all at the same negative pressure, you're not going to get air passing between units because there's no pressure difference between them. But what we found when we logged pressure in apartments over time and monitored window opening was when people open windows, the pressure in the middle apartment, for example, drops to close to 0, and you get free exchange of air in and out of the apartment. You also, when someone opens a window in that apartment, that affects the pressure in the neighbors, and so the depressurization in those neighbors decreases. So what happens if someone burns a grilled cheese sandwich? That pollution that comes from that apartment, this middle apartment is now at 0 pascals, and the other apartments are negatively pressurized with respect to that one, and so is the corridor. And what we found was air was flowing out of this apartment with the open window, down the corridor, and into the apartments with that were still negatively pressurized. So this is obviously not a good situation. Someone generates pollutants in their apartment, they try to ventilate it, and it ends up going into everyone else's apartment. It's not good, but unfortunately this is a pretty common phenomenon. So the idea with trickle vents and passive vents is to provide a known source of makeup air. There's pictures here of trickle vents, and then on the right is an airlet by American Aldi's. Both of these go in the exterior envelope and draw air straight from outside. So we tested passive vents, both airlets and trickle vents. Here you can see me expertly taping this cardboard box around a trickle vent. But we're depressurizing a trickle vent and monitoring the flow and the pressure at the same time. And so the idea is to get a performance curve for a trickle vent as it's installed. So this is data from one building of 5 trickle vents. The blue line shows performance from these 5 trickle vents at various pressures, and then the line above it is the same model of trickle vent done in a laboratory. So ours differ from the lab results, probably for a few reasons. Maybe my cardboard box isn't completely airtight, but there's probably also some other factors that are contributing to this. In some buildings, we find that performance of the trickle vent is actually affected by the way it's installed. So in case you don't know much about trickle vents, many of them actually come in two parts. They have an inside part and an outside part. The outside part is more like a rain hood and a screen, and the inside part is a little operable vent that you can open and close. And the outside hood goes on the outside of the window frame, and the inside goes on the inside of the window frame. And the trickle vent manufacturer sends this assembly to the window manufacturer, and the window manufacturer cuts a hole through the window frame and attaches the two parts of the trickle vent to the inside and outside. So there's supposed to be a clear hole between the inside and outside, but you can see from these pictures that there's obviously not a clear hole between inside and outside. You can see light through some of these drill holes, but obviously there's a lot of fiberglass here in the way of airflow. So some of the trickle vents we test perform nowhere near their specification. So we're often asked by architects, how do you specify a passive vent? And it's kind of a tricky question because you need to know a lot of things. You need to know how tight the apartment's going to be, how well weather stripped the door is going to be, and how airtight it is. You need to know the flow rate of the exhaust, not just how much is on the plans, but how much is actually going to be withdrawn from the apartment. And then you need to have a good idea of the trickle vent at this expected pressure that's going to develop in this building that's not built yet. So it's a pretty difficult thing to specify a trickle vent when the building is not built yet. So the standard procedure is to put one trickle vent in every room. So common trickle vents are about, they can range in size, but we see a lot of them that are about 4 square inches of nominal opening per vent. And if you compare that to a common apartment, blower door test from a common one-bedroom apartment, it could have as much as 70 square inches of total leakage, not including the trickle vents or the door leakage. So that's, by comparison, the amount of leakage, the amount of free area from a trickle vent is a lot less than the free area from the rest of the envelope. And so if you're depressurizing the envelope with the hopes that air will come through only the trickle vents, you've really got to reduce your leakage in order to make sure that it comes from the trickle vent and not from other places that you don't want. So we tested the performance of passive vents in 2 buildings and then monitored pressure over a couple weeks. And we also did some other measurements at each building. So 2 example buildings, the first one with trickle vents and the second one with airlets. The first one had fairly airtight apartments, 2.5 ACH 50, and the other building had much leakier apartments, an average of 6.7 ACH 50, so much, much leakier. The exhaust rates were fairly similar per apartment, the average of 41 and 53 CFM, but you can see that the tighter apartment, the performance from the passive vents is a lot better from the building with airtight apartments than it is from the leaky apartments. So obviously airtightness has some effect on the ability for passive vents to draw fresh air in. So we tried to do this again in a building with trickle vents but some super tight apartments. So this chart here shows the results from 9 blower door tests. These apartments are all near each other. This the bottom row is the second floor, apartments 201, 202, and 203, and on top we have 401, 402, 403. So 4 out of 9 of these apartments received enhanced air sealing, and the numbers are really a lot lower than the unsealed apartments. You can see in terms of CFM 50 per square foot, they're all below 0.1 CFM 50 per square foot, which is a lot lower than many apartments can achieve. So putting this in perspective for a lot of blower door tests. We've done many compartmentalization tests over the years. Compartmentalization test is a single blower door in a single apartment and depressurizing only that apartment, and the doors and windows to the neighbors are open during this test. So it's single apartment test. So we've done lots and lots of these for various green building and utility programs such as LEED for homes. So this is a histogram of some of the results. So you can see that the great majority of them, thankfully, fall below the thresholds required for Energy Star for multifamily high-rise and LEED for homes. That's the threshold that they need to meet in order to qualify for the programs. LEED NC has a much tighter threshold, but still a good number of apartments can meet that as well. This is an approximation. But the apartments in our study, some of them are very tight, and then the rest of them are pretty standard air tightness. So what does that air tightness get us? Well, in terms of operating pressures, the sealed apartments are generally a lot more able to draw air, to depressurize the apartment and keep them depressurized. The apartments in red, these are the operating pressures we just sampled on a random day. Sorry about that. Oops. We sampled these apartments on a single day, and I honestly can't explain what this and why one of these apartments is at -4 while this unsealed apartment is at -12. But generally, when we did this single point test, the sealed apartments were able to develop a much stronger negative pressure than the unsealed apartments. So when we do this test, the trickle vents are open, the bath fan is running, exhausting air, and the apartment door is closed tightly, and so are the windows. So this picture on the right shows a data logger that we use to monitor these pressures over a couple weeks' time. So hopefully we'll get some more data here to confirm this suspicion that tight apartments can hold pressure better than leaky apartments. So this is these are some tests over about a 10-minute period in 2 different apartments among this group. And to explain the chart a little bit, what we did was we stood in the apartment with data loggers and manipulated different systems in the apartment and watched what happened. So in the first condition, we turned the exhaust fan off and just logged the ambient pressure in the apartment with nothing going on. Then we turned the exhaust fan on, but closed the trickle vents, closed the door, closed the windows, and this is the maximum pressure that you would see in this apartment under any conditions. Next, we opened the trickle vents, and that relieves some of the pressure generally. And then we also cracked open the front door to the apartment, the corridor door. And the reason we did this is that sometimes, since we're logging in a building in which people are still working, sometimes they enter the apartments and then forget to close the door tightly. So we want to know, what does it look like when this door is just cracked. And then we close the door again, trickle vents are open, exhaust fans on. That's state number 5, and then number 6 is we turn the fans off again. So in the standard apartment, you can see a couple things. First, the pressure across the trickle vents, which is the exterior pressure, this blue line in the graph on the top, is pretty much close to 0 all the time, which tells us that there's pretty much no airflow coming from the trickle vents at any time. By contrast, if you look at the apartment below, the highly sealed apartment, if you do anything in that apartment, the pressure changes. So look what happens when you turn the fans on and close the trickle vents. The pressure goes all the way to -15, but when you open the trickle vents, it drops to, raises to -12, and that's the normal operating pressure of this apartment. So -12 means you're going to get 12 pascals across that trickle vent, and that's pulling air in from the trickle vent pretty much all the time. Even when you have the door to the apartment cracked open, you're getting pressure across the corridor door and across the envelope, so it's still drawing air from the trickle vents. So it's pretty clear that in this one building, you compare one standard apartment that's sealed to, say, Energy Star standards, and then you compare it to this super sealed apartment. There's the pressure response of these two apartments is totally different. So what we're trying to do is quantify these airflows. So we're using Energy Conservatory Flow Blaster for fan flow measurements from the exhaust fan. We're using pressure measurements for the trickle vents, and the same for the door. We measure the door leakage as well. And then we use data loggers to watch this pressure over time and see how this building reacts over the long term. So I want to make a distinction here about the different kinds of leakage that we're talking about. We have blower door tests that pretty much, a blower door test will give you leakage from the exterior envelope, interior envelope, and the corridor wall, but it won't give you leakage, the leakage value of the corridor door or the trickle vents. So that's one number. Then when this building is put into real operation, those pressures go away and you have prevailing building pressures, which for some of the, if everything is working as it should and your target apartment is at -5, for example, like we had in the example before, and your neighbors are all at -5, some of the leakage between those apartments will be eliminated because there's no pressure difference between those apartments. So some of the leakage that is accounted for in a blower door test is not actually functioning as a leak in normal operation. So really functional leakage is limited to those surfaces that have a pressure difference during normal building operation. So how does this all translate to airflow in these target apartments? Our research is still ongoing. We still have data loggers in these buildings, so we don't have all the data to show you what an actual apartment is, but this is an ideal apartment. And if we just divvy up these leakages, we can see how they amount to airflow through the exhaust fan. So the blower door test numbers, the total of all of these leakages here is 110 CFM. And however, so this is the only number you get from your blower door test, 110, but that number is divvied up between several surfaces. So the exterior envelope, these are just arbitrary designations, but maybe good guesses about how much of a blower door number comes from each surface. So the exterior leakage might be 20% of the total blower door number, and the corridor wall might be 20% of the total. But the interior, two interior walls and the floor and ceiling might amount to 60% of the total leakage. So that's how these are divvied up for this example. And the reason this is important is that some of these leaks are functional and some of them aren't in normal building operation. So the exterior leaks, those do have a pressure difference across them during normal building operation, so that's a functional leak, but the interior walls hopefully should not have pressure differences between apartments, so those are not functional leaks. So we have to test the door leakage separately, but when we do, we find for a very tight apartment, very tight door, you can get those down to about 20 CFM 50. Typical unweather strip doors might be well over 100 CFM 50. Trickle vents, if you really do have close to 8 inches of free area, you could expect maybe 65 CFM from that trickle vent. This is using that chart from the manufacturer that we looked at before. So about 65 CFM coming from the trickle vents. At a normal building pressure of 10 pascals, these flows at 50 pascals drop considerably, so the total of the functional leaks as a total of the exhaust, the controlled makeup air fraction, you've got the amount coming from trickle vents is 29 CFM out of a total from the fan of 58 CFM, and that controlled makeup air fraction is then 50%. So this is a theoretical apartment still at this point. We don't actually have an apartment that is this tight. We have some of these apartments that we sealed tighter got close to 110 CFM 50, but they didn't get totally there. So the tightest one was 127 CFM, I think. So we're still not there. But this is the amount of air tightness that might be possible, might be required to make trickle vents work like they should. And how do we get them that tight? Basically, we cheated. We collaborated with UC Davis, who Mark Modera and Curtis Harrington at UC Davis are developing an aerosol process similar to AeroSeal that uses atomized building sealants. You can see in this picture in the middle, you've got a mist spraying into the apartment. It's actually water in that picture, but it looks similar when this is going on. So you put a blower door in the apartment door, and you pressurize the apartment to up to 100 pascals, and then you put these injectors in the apartment and spray this mist into the air, and the mist finds its way towards the leaks, and it sticks on the corners of the leaks and eventually plugs them up. So you can see it's pretty effective. So although it took us quite a bit of time to set up our data loggers and everything, which wouldn't normally be done, we still averaged 75% leakage reduction in these apartments over an hour and a half. So it's pretty dramatic. So we started with the same types of apartments that we had in the rest of the building, and you can see on the chart below that leakage just drops and drops and drops and drops until it approaches sort of a minimum leakage. And so this is pretty exciting. So this aerosol sealing does really well at compartmentalizing each individual unit, but it also seems to have an impact on the neighbors. So the middle apartment and the lower right apartment also seem to be benefiting from the aerosol sealing of their neighbors. So this is a pretty cool technology, and we hope to work more on this in the future with UC Davis. But is this available to the greater market? Not really. Let's look at this graph again. We think that the air leakage, the air tightness necessary for passive vents to work is somewhere around here, where close to where we are right now with these aerosol sealed apartments, but not sure that this is something realistic for the industry at large. So conclusions that we draw from this is that from the air pressure monitoring that we did, and I think all of you will agree, compartmentalization is beneficial for the operation of the building overall. And if you've ever tried to specify or test a trickle vent, you realize that getting actual in-field performance of these is very important but difficult to do. So we think that passive vents can function if you put them in extremely tight apartments, but is this something that we want to be recommending for the industry at large? I think we'll leave that for the group discussion, and I'm sure Joe has some comments on whether this level of air tightness is achievable on a wide scale or whether it's even advisable. So, and that's it. That's it for me.
Hello, everybody. Sean, thank you for those nice words at the beginning of your presentation, and thank you for sharing what I think is some pretty fabulous work. I'm going to be presenting from a slightly different perspective. I don't believe that if we have reasonable compartmentalization that any form of exhaust-only ventilation is possible or practical or functional. Next slide. I love the phrase build tight, ventilate right. This comes from Jim White almost 35 years ago. Next slide. The question is how tight and what's right? From Sean's work, as well as other work in that we've done, a lot of work that has been done by Canada Mortgage and Housing Corporation, Duncan Hill's work, and some of the RDH work in Vancouver, we're pretty clear that the 0.3 CFM per square foot at 50 pascals is a reasonable, achievable metric that results in significant tightening of buildings. That 0.3 is very close to 3 air changes per hour at 50 pascals for a typical compartment. The 0.3 is also now the ASHRAE standard 62.2 compartmentalization number. So I think we're pretty close to deciding how tight is practically achievable. The question of what's right now needs to be addressed. Next. We can't rely on infiltration in a compartmentalized apartment. We have in essence a six-sided cube, and for all intents and purposes the only side that we can rely on for that air is the external surface. This is a staggeringly difficult problem to resolve with exhaust systems. Next. These are the metrics that have been bandied about for many years. 0.02 for materials, 0.2 for assemblies, and 2 for enclosures. The 2 for enclosures is, as I've mentioned, is pretty much where we've settled. or where I see the consensus appearing, and then again that's around 0.3 CFM per square foot at 50 pascals, and that corresponded very nicely with Sean's histogram and the results that we're seeing from other parts of the country. Next. To put this into perspective, 3 ACH is getting rid of big holes. 1.5 ACH is very difficult, but it means getting rid of small homes, and the 0.6 is unbelievably difficult to achieve, and it's the German passive house number. I think that's neat if you're wanting to be the member of a select club of people who like to make things incredibly tight, but it's not a reasonable number from an industry perspective. Next. So build as tight as possible with balanced ventilation. That's where the engineering side of me, or the engineering side of our firm, is in our experience has ended up as tight as possible from a practical perspective. Seems to be the 3 air changes per hour at 50 pascals, the 0.3. Now the boxes or the cubes, the compartments are so tight that the only system that we're finding that actually works is one that is balanced. The amount of air that's being brought in is balanced by the amount of air that is being extracted, and this is done with interlocked fans or mechanical ventilation. This is especially the case now that ASHRAE standard 62.2 has significantly increased the ventilation rates since, well, in the last 4 years, it's resulted in the net doubling of the ventilation flow. So we're talking about 50 to 60 CFM of continuous air change, and at those flow rates, at 3 air changes per hour at 50 pascals, or the compartmentalization number, we're talking about 20 pascal to 30 pascal continuous negative pressures if we're talking exhaust ventilation. With balanced ventilation, of course, we don't have the negative pressure. So we know that we're going to go to a highly negative condition if we don't have balanced ventilation. The question is a highly negative pressure desirable or acceptable? There isn't consensus on this. I think that we have some serious issues with those kinds of high pressures or high negative pressures. I have decided to abandon that approach from an engineering perspective. So balanced ventilation is the place to go with some form of distribution or mixing within the compartment or within the building, and coupled with source control, spot exhaustive ventilation, advanced filtration or enhanced filtration, and materials that don't give off bad stuff. At the very end of this, balanced ventilation makes energy recovery possible. That's not the most important thing. The most important is the balanced ventilation with the distribution coupled with the source control, but it's nice that with the balanced systems, energy recovery is possible. Next. This is a classic HRV. We don't see a lot of these in multifamily construction. I think we're going to be seeing a lot of these in multifamily construction. The current problem with the industry is that the systems are much larger than they need to be. We're talking 150 to 200 CFM systems where we really want 50 to 75 CFM systems or even smaller. Next. A more brutal way of doing it, not as elegant, would be to have outside air coupled to the return side of the air handler, where the air handler is always operating at a fixed speed, and that is coupled with exhaust fans that are also continuously operating. So you in essence have, say, 2 bathroom fans operating each at 25 CFM continuous, coupled with outside air being brought in at 50 CFM, and you have a fully balanced system. This is not as elegant as a balanced HRV or ERV, but it certainly works. The energy penalty, of course, is you want to have a highly efficient blower motor to do this. ECM motors, of course, we have. And one of the advantages of this is that we can have very high filtration with the central air handler, and that has some very nice advantages. Next. Architects hate this image. We're basically poking lots of holes in the facade. Each compartment needs an air inlet and an air exhaust from a decentralized mechanical system approach. Next. I don't view this as horribly aesthetically bad, but apparently I have no taste and I just don't understand aesthetics. The engineer in me views this as something beautiful. I guess this is why this perhaps explains the historic problem between engineers and architects getting along. These balance systems came out of necessity in extreme climates, such as hot, humid places, such as the coast of Florida, with condominium construction. That was the only way to handle the humidity issues, and each apartment or compartment also had to have supplemental dehumidification. Next. Here's our attempt at minimizing the number of holes, ganging a number of exhausts in one particular hood. Next. A effective, low-cost, and not particularly elegant way of providing supplemental dehumidification has been to locate a standard off-of-the-shelf dehumidifier inside the return closet. It's cheap, it works. What could be possibly bad with it? Well, it's not ducted, and a number of programs such as LEED discourage this. Next. It's possible to have such a system with a fully ducted return as opposed to a return closet. You're just basically going to be extracting air from the closet through your return system. So, the approach can be made to work without an awful lot of cost. Next. This is not a beautiful looking thing. In fact, this is so unbeautiful looking that a lot of projects, the contractors actually put the chintzy, cheap-looking dehumidifier in a sheet metal box to make it look industrial. And apparently, it's not exactly Intel inside, it's dehumidifier inside. Next. When you don't have a distribution system, it's not unusual that a dehumidifier is located in, for example, a linen closet with a louver door. As amazing as this seems, it has been proven to be effective. It's based on work going back 20 years where we've been called upon to handle part load humidity problems in these small condominium and apartment units in Florida and in Texas. Next. Washers and dryers. I don't think people understand that you can't put a 200 CFM exhaust dryer in one of these apartments. These apartment units that are at 3 air changes per hour at 50 pascals or 0.3 CFM per square foot at 50 pascals, they go to 50 to 60 pascals negative. Basically, exhaust dryers don't work if you compartmentalize in these particular apartments. And so the only technology available, well, there are two. One is practical and the other is yet to be figured out practically. One is a condensing dryer, but there isn't a vent to the outside. And the other is providing a dedicated interlock makeup air fan into the room or the space that the dryer the exhaust dryer is functioning. Easy to say, not easy to do. Next. That brings us to one of my all-time favorite controversial subjects. You can't put a kitchen hood that is extracting at 1 to 200 CFM into one of these apartments without providing interlocked makeup air, which is why most apartment units don't have kitchen exhaust hoods. They have recirculating hoods, and I view recirculating hoods similar to a toilet that never flushes and just swirls the effluent around and around and around. If we're going to want exhaust hoods over cooking surfaces, which for the record I believe are desirable and necessary, especially if we're dealing with the PM 2.5 issue. I applaud LBL's work in this regard. We're going to want high capture efficiency. We're going to need flow rates that are probably between 1 and 200 CFM, and that's going to require interlocked makeup air. If you're going to do interlocked makeup air needs to be introduced at the bottom of the cooking surface. You have to have a hood that's wider than the cooking surface and deeper than the cooking surface. You know how to do this from the experience in restaurants. What we are in essence doing is simply downsizing the standard practices in a well-designed commercial kitchen. Next. From an engineering perspective, making the hood bigger and deeper and introducing the makeup air is fundamentally straightforward. It's not the easiest thing to incorporate from an aesthetic perspective and a practical perspective in a small apartment that doesn't have the space available. You can't have 100% of the makeup air delivered under the unit. You're required to have a zone of negative pressure at the cooking surface, so you tend to provide 70% of the makeup air under the unit, and then the remaining 30 goes into the general space. So when we design these systems with an interlocked fan that's bringing air in from the outside, let's say that the exhaust flow at the hood is 100 CFM, we're providing 100 CFM of makeup air, we would deliver 70 CFM underneath the unit and then 30 CFM of that 100 into the general space. Next. In a house, it's fairly straightforward to do. You introduce it through the floor. That's not a practical technology in an apartment. Next. Just to demonstrate how much of a hypocrite that I am, this is the exhaust hood at my house. It's very, very, very attractive and totally non-functional because it doesn't have enough of a capture efficiency, but it does look good. Next. This is my proposed retrofit. I am having a great deal of difficulty selling this concept to the architect of record who I share the space with. Next. So what are we faced with? The bare minimum that we're seeing that actually functions is outside air to the return side of the air handler that's interlocked with continuous exhaust at the bathroom in a recirculating kitchen hood, which again, for the record, I dislike intensely. But this is what we're likely to see with 3 air changes per hour at 50 pascals with the ASHRAE standard 62 ventilation rates. Next. South of the Mason-Dixon line, we're going to end up having to add supplemental dehumidification. And the reason is that the loads are so low in these units and the outside air change rate is so high, the latent load is at the point where no typical coil design or air conditioning system is capable of handling. And so we are seeing and have been seeing for many years now the need for the supplemental dehumidification system. It's not elegant, but this is the least expensive approach that apparently are seeming to us is working. Next. The idea of having a kitchen exhaust hood to the outside is a non-starter with the tightness that we're seeing. Next. A dehumidifier doesn't help us. Next. What we need is an interlock makeup air system with the kitchen hood. We know how to do this, but this adds another hole in the wall. I think that was a Pink Floyd song lamenting the fact of makeup air. With this approach, you're going to have the outside air to the return side of the air handler. The air handler is operating continuously, and it's basically operating in conjunction with continuous bathroom exhaust. This is what I would view as the minimal acceptable approach, and then you have basically condensing dryers. Next. You add the dehumidifier south of the Mason-Dixon line. Next. This is a much more elegant approach. It provides heat recovery. We're now, in essence, not relying on the air handling unit itself to do this air change. What's nice is that you can get rid of the furnace air conditioner completely and go with radiant heating or a package terminal heat pump, and the general system works the same. Next. Even with an ERV, a dehumidifier is going to be necessary because an ERV does not dehumidify. It maintains humidity but doesn't create the dry conditions. So the air conditioner provides the cool, the dehumidifier provides the dry, and the ERV maintains those conditions. There's a lot of misunderstanding of what an ERV is capable of doing versus not doing. Next. We see a lot of this in the Pacific Northwest. The nub is that this won't work with the kitchen exhaust without having an interlocked makeup air system. Next. As we go down the coasts, we're finding that people are adding package terminal heat pumps. That provides both the heating and the cooling. HRV, ERV, pretty slick system, but the problem child is still the kitchen. Next. I don't know of any way of getting around the interlocked makeup air for the kitchen exhaust. You sure as heck don't want to run it through your HRV or your ERV. Next. And man, south of the Mason-Dixon line and east of Interstate 35 in Texas, that whole miserable region of the country is going to need supplemental dehumidification at the flow rates we're talking about under ASHRAE and under LEED. We're going to just have to suck it up and accept that, or we're going to have to lower the rates. Good luck with that approach. Next. Get used to condensing dryers. 200 CFM of exhaust from a standard dryer isn't in the cards anymore. And I have yet to see a practical makeup air system that's interlocked with a standard dryer. Next. Once we achieve the compartmentalizing of the units, we got the corridors and the hallways and the elevators to deal with as well. The implications of this are multifaceted. It's not just the compartment. Next. It's nice to have the elevator under a slight negative pressure. You're going to need to provide some form of makeup air, and that makeup air is going to be typically introduced into the corridors. And this air is generally not going to be conditioned, and it really doesn't have to be because the flow rates are exceptionally low. We're talking maybe 15 or 20 CFM per one of these long corridors. And what's nice about that is you can just simply use dilution mixing of the air in the space to partially temper this air. Next. There's a 3% leakage requirement at the top of a shaft per elevator car. This goes back a century with respect to smoke and fire control. That hole defeats the entire purpose of control, and the only solution is to have an interlocked motorized damper that's connected to the fire control system. So you get rid of the big passive hole at the top of your elevator shaft with a motorized damper that's always closed when the power is energized. When there's a power outage, the damper opens, or when there's a call for fire or a fire call, the damper opens. And this is separate from an exhaust system that constantly creates a slight negative pressure. The airflow regulator is necessary because of the stack effect. The flow rates are going to vary seasonally and with the height of the building. Next. This is what they look like. This is now common practice in Florida, particularly because this has been a major problem for unconditioned humid air from a mold perspective. Next. As strange as it seems, some people are determined to overventilate the corridors and overpressurize the corridors, and that's going to require preconditioning of the air because it's almost 100% latent load, and there's no sensible load in these corridors because they're not usually seeing any exterior walls. This is not an easy answer. Next. Trash chutes, they got to be negative. Got to suck. Next. I've seen in the hotel industry the interlocked of, basically air from a rooftop supply to corridors with smoke dampers at each floor balanced with exhaust from the elevator shaft. This is sometimes coupled with energy recovery as well. Next. There's the energy recovery. This is for a premium building. I see this rarely, and when I do, a little tear forms the corner of my eye as I'm so excited to see something like this. Good luck. Next. This is a Florida solution, preconditioning the air. Next. We often see ceiling-mounted systems that have no outside air. They don't introduce any outside air. All they're doing is providing some moderate tempering or conditioning in extreme climates. Next. Next. Here's the trash chute. We have to have that at a fairly high negative pressure for obvious reasons, and the trash room itself has to be even more negative. And this requires compartmentalization. And one of life's ironies, the highest negative pressures in the tightest compartments need to be around our trash. Next. It was a dream of a number of us over the last 30 years to be able to put our elevators in vestibules. Whenever we put them in vestibules to compartmentalize the building from a stack effect perspective, occupants tend to defeat the best engineer by leaving the doors or prying the doors open. I've come to accept the fact that this will probably not occur in my lifetime, and so from an engineering perspective, it's a desirable thing to have, but from a constructability and occupant perspective, occupants don't like it. Next. 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 Apparently,
that's your last slide, Joe.
well, apparently I'm done.
Okay, thank you.
Okay, we'd like to thank our presenters for those great presentations, and we have time now for a few questions. We already have some great questions from the audience, and you may submit additional questions through the questions pane on your screen. The speakers will answer as many questions as time allows. So the first question is for Sean. Why is the manufacturer's data for trickle vents so much different than yours?
Well, I tried to show that there's often differences between the installation in a laboratory and then the installation in the field. We're going to be doing more trickle vent tests on this current study building where we're going to test the airflow through the trickle vent and then compare it to the manufacturer's data. But we're also going to take it apart a little bit and see how well it's been constructed through the window frame, because I think that has a big impact on how well they function, is how much the trickle vent might be nominally 4 inches of leakage, but if the window manufacturer didn't cut the holes exactly right through the window frame, you might have less than that. So that could be one reason why the data is different. We are also going to try a different method, which is the method we were using to test the trickle vents was basically putting a suction on the trickle vent itself and measuring using a low flow plate on the duct blaster, so down to 1.4 CFM. But we're probably going to do a pressure equalized method, so the measurement instrument, whatever measurement instrument we use, is not going to be affecting the measurement. So I think we're hoping to get even more exact numbers so that we can confirm that it's not, confirm whether the field installation equals the laboratory results.
Okay, and then there was another question about trickle vents. We have heard that tenants do not like the trickle vents, especially in cold climates such as Chicago, and they will cover them up. Have you encountered this?
In many, many apartments that we've gone into, people have no idea what those things are, and they're usually closed. They're usually closed, and then people often open the windows regardless. So I would say that the tenants need to be educated on what they're for, but it's also possible that it's just not providing enough fresh air. So I haven't heard so much that people close trickle vents because they don't like them, but I think they just a lot of times don't know what they're for. It is definitely possible that trickle vents and other passive vents like airlets, if you don't install them according to the manufacturer's instructions, that is, we've been in some buildings where they put the airlets near the floor for architectural reasons. The manufacturer's instructions call for them high up on the wall so that a draft isn't drifting over people's feet, but in some buildings they put them low, and then people complain about cold drafts, and that's just because there's cold air leaking right near your feet. So that's another reason people would close them up, is because of comfort problems.
And here's another question for Sean. Do you think that the super sealed apartments will be stuffy?
Don't know yet. We're going to hopefully conduct some humidity monitoring. But yeah, it's possible that with the super sealed apartments, they could be stuffier, especially if the trickle vents aren't pulling enough fresh air.
And another question regarding ASHRAE 62.2 and its adoption by the IBC. Should the requirements vary by climate region across the country? So for what's needed in New York, Anchorage, Vegas, and Taos would differ.
Joe?
Sure. Give me the easy one. Yeah. No, the logic for that makes no sense. But this is in response to what I view as an overventilation number to begin with. There's pushback because of comfort issues and humidity control issues in the cold climates and the hot, humid climates. And that simply tells us, from my perspective, that these flow rates are not achievable from a dilution perspective without some kind of a comfort or energy penalty. And so the idea is that, well, gee, let's reduce the rates because we've created a problem with an excessive rate in a cold climate and an excessive rate in a hot, humid climate. Well, you have to ask yourself, well, where did the rates come from in the first darn place? I thought it was to control contaminants, and that's how the rate was established. So if we can reduce the rates in the hot and the cold climates, why can't we reduce them everywhere? Interesting philosophical question. In the past, the argument was that we could reduce the fan rates in cold climates because the stack effect in the wintertime compensated for that. And that was actually a reasonable way of looking at it, except now our enclosures are so tight that the infiltration component to the stack effect doesn't compensate for that. So I tell the committee that you can't have it both ways, and that's not exactly a popular position at this particular point. In terms of whether or not the codes are going to accept this, there is no possibility that the IRC is going to accept ASHRAE standard 62.2 in its current form because of all of the problems with part load humidity and dryness and the actual practical issues of providing these flow rates. There's going to have to be a significant change if you're going to see code adoption by the IRC. Having said that, That doesn't mean that ASHRAE 62 can't become basically the standard in certain states. It's already been adopted, for example, in California, which, by the way, is paradise from a mechanical engineering perspective and construction perspective. I don't see it being adopted in Illinois, and it's certainly not going to be adopted in Florida. But that doesn't mean that you also can't have programs adopting it, such as LEED or Energy Star. I think that there's going to have to be some movement on all people's parts, on all sides, in order to see that standard move forward and see more wider acceptance. But to change the rates based on climate conditions is basically a band-aid for a standard that isn't workable at this point in time.
Thank you. Here's another question for Sean. Were the tracer gas tests conducted to determine those airflow patterns from apartment to hallway to neighbors?
Well, they weren't tracer gas tests. We just measured pressure differences over time. So we used data loggers that measured Pascal differences between the different zones. So each apartment had pressure sensor across the exterior window and then one across the corridor door, and we did this in several buildings. So if you just do some addition, you know that the pressure in the corridor is basically the same, the length of the corridor. So if it's +5 in one apartment and with respect to the corridor, and it's +4 in another apartment with respect to the corridor, then you know there's a pressure difference between apartment A and B of 1 Pascal. So that's how we made those measurements.
Okay. And Sean, can you talk a little bit more about the aerosol process? How long does it take, or how much does it cost?
Sure. Well, we spent a lot of time trying to figure out how much it costs, and we still don't know. I'll have to actually defer to Mark Modera and Curtis Harrington at UC Davis for more info, because it's really their project. We were just lucky to get them to come out here and try it on one of our buildings. We hope to collaborate in the future, but this was just we just did 4 apartments with them. So those 4 apartments, it took us some time to set up, especially all our data loggers and then our tests. We did sound transmission measurements between apartments and lots of pressure tests and diagnostics. So it's a very, very cool process and very interesting for a research tool, actually. But as it is right now, it takes a while to set up. So you need a air compressor, you need a pump for pumping the sealant. You need hoses, compressed air hoses, you need nozzles. You have to close up the entire apartment, protect surfaces that are, we did this in very rough stage construction apartments, so those airflow rates they got down to less than 0.1 CFM 50 per square foot when it was just drywall and there was no outlets, no baseboards, no floors, nothing, basically. So this is done in a very early stage of construction when it doesn't matter if you get this sealant dust on the floor, which is kind of sticky. So it's a very cool process. Right now it takes a while to set up, and I think part of their ongoing research is to refine how they do the process so that it gets faster and faster. And the idea is to be able to use something like this as a contractor. Since it takes some setup time, you could maybe set up in one apartment and do 4 or 5 other apartments, just do them one by one day. So maybe it would take, we were estimating something like 4 man-hours per apartment. But if you consider that from a very basic level of air sealing, which gets you just under 0.3 CFM 50 per square foot, to very compartmentalized apartments, 4 man-hours is quite a bargain. So we're excited about it, and we hope that we get to collaborate with them in the future.
Thank you. And now I have a few questions for Joe. Can a balanced system operate intermittently and still be effective or compatible with multifamily buildings?
Yes. What's nice about balanced systems is since they don't affect the pressure in their individual compartment, they won't affect the pressures in the neighboring compartments. It's as if the compartments don't know that they're beside one another. And so intermittent balanced ventilation certainly is compatible. The question is what's the off-on time sequence, because at some point you're going to have to increase your intermittent flow rate in terms of the contaminant capture and removal. ASHRAE 62 has got a nice way of dealing with that, and so there's a technical way to allow that or accept that. And quite frankly, that's right now with an HRV and an ERV, that's the only way that we can really do it, simply because the units are so large. They're providing way more flow than you actually need in most of these apartments. So half-time operation or 30% operation or 20% duty cycle is not unusual for these types of systems.
And one of the attendees had a question on slide 11, the image of the building with inlet and outlets. Those are close to the windows. How do we avoid exhausted air coming back through an open window?
We don't. There will always be some entrainment, but it's not particularly significant. That's been shown with tracery gas work by lots of folks, and unfortunately I can't think of any reference at this point, and so those folks are going to be irritated at me for not remembering. But yes, there will be some re-entrainment, but in the grand scheme of things, it's minor compared to all of the other issues that we're struggling with.
Okay. Why is it that the kitchen needs 75% makeup air from below and 25% from general space? What standard specifies that?
Well, there is no standard. It's basically engineering experience and judgment. The rationale is to have a region of negative pressure at the cooking surface. If you just have a complete balance, you're not going to have the zone of negative pressure. The physics of this, the practice of this, is explained in ASHRAE applications. So the ASHRAE applications handbook shows this. It's not a standard, it's just there it is. There's the testing that was done. This was done, I believe, by the California Energy Commission. It's a fabulous piece of work. I urge people to read that section on commercial kitchen ventilation design, and then downsize the thinking for residentially. And it's somewhere between 60 and 70%. This seems to be working from the smoke tests that we've been doing and some of the custom home designs, that when we get a chance to actually have an unlimited amount of money and we actually get to control or have some impact on the aesthetics of these systems in these high-end houses.
Okay, and then a final question. If I have no choice and have to run my exhaust up to the roof, how can I minimize the issues? In the same vein, can I bring my supply down from the roof? What do I have to consider when I do this?
If the ductwork is ultra tight and the connections are where the ducts penetrate the floors are also ultra tight, you can get very, very good control. this was shown, I guess, with a lot of the compartmentalization work and testing that I think Sean's group talked about or already has done. So it's more difficult to do, but it's achievable, and you basically want to have very high pressures in the ducts to provide control, because you're fighting the stack effect seasonally.
Okay, that's about all the time we have for questions today. Panelists, before we take our quick survey, do you have any additional or closing remarks you'd like to make before we close the webinar?
Not me. This was great.
Okay.
Neither. Thank you. Thanks for allowing us to participate.
Well, thank you again to the panelists. And now we'd like to ask our audience to answer 3 short questions about today's webinar. Your feedback will help us to know what we are doing well and where we can improve. The first question asks whether the webinar content was useful and informative. To answer, click on the radio button right in the Go To Webinar panel. And the second question asks about the effectiveness of the presenters. And the next question asks whether the webinar met your expectations. Thanks for taking our survey. Stay tuned for the next Building America webinar on October 23rd, which will begin our series on high-performance space conditioning systems. Visit the meetings page on the Building America website to register. On behalf of the Building America program, I'd like to thank all of our expert panels today for their time today, and our attendees for participating in today's webinar. We've had a terrific audience, and we very much appreciate your time. Please visit the Building America website to download a copy of the slides and learn more about the program. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America webinars. This concludes our webinar today.